Greetings everyone and Happy New Year. I hope you all had a wonderful holiday season and that you're excited to get back into another year. I'm sure I'm not the only one who missed our December math fix, so without further ado, let's get started. Today's math fix is brought to you by F.IF.2, which asks students to use function notation, evaluate functions for inputs in their domains, and interpret statements that use function notation in terms of a context. Let's take a look at our problem today. Students are asked to determine the different seating arrangements for the 189 people that have RSVP'd to attend a school banquet, given the parameters that the cafeteria can accommodate up to 15 rows of 9 tables, if all of the tables are pushed together. They are then asked to describe these different seating arrangements with an equation. Where might students start with this? Let's jump in. Students might initially assume that they must push all tables together, and that automatically is the best option. Given this, students might start by sketching out a row of 9 tables pushed together to figure out how many people they can seat in one row. If they seat people on all sides of the table, they will end up with 20 people in that row. Once they figure this out, they might sketch more rows of 9 until they get close to 189, so 9 rows of 20, which makes 180. They will then need enough tables to fit 9 more people. Pushing tables together again would mean they need 4 tables to seat 9 more people, and that would give them 1 extra seat. In order to describe the number of people seated as a function of the number of tables, students could write an equation for each row where x is the number of tables per row, so f of x equals 2x plus 2. In this case, for the number of tables you have, you can seat 1 person on each side plus 2 for the people on each end. There are also many other ways to write this equation and connect it to the context, so you could challenge students to find those other ways. Students might be tempted to stop with this seating arrangement. However, there are other factors to consider. For example, if there were a speaker, they might want as many people as possible facing the front. In this case, they might only seat people on one side of the row and on the 2 ends. Doing this would allow them to seat only 11 people per row. Given that the cafeteria only allows 15 rows, this arrangement would only allow 165 people to be seated. Describing each row with a function would give you f of x equals x plus 2. However, one option that has not yet been explored would be to pull tables apart. This is where things get interesting, as we do not have exact measurements for the tables, therefore we cannot know exactly how many tables might fit in the given space. For our purposes, let's assume that we can just leave a tables width space between the tables and fit 5 tables per row if they are not pushed together. In this scenario, we can actually fit more people per row than with the tables pushed together. More people are sitting sideways, but we can fit 15 people without having anyone's back to the front. In this case, we have more than enough room for the 189 people, as 15 rows of 15 people gives enough seats for 225 people. This scenario might be best described by the simple function f of x equals 3x. One extension might be to ask students which seating arrangement will allow for the fewest number of tables, or to change the shape of the table. We never said that they had to be squares. What would happen if there were triangular tables or pentagons? It turns out that there is a pattern within the rule for different shaped tables. I challenge them and you to discover it. And there you have it, folks, the January math fix. As you know, we love hearing about what you're up to in your classrooms all around the globe, so don't hesitate to share with us your take on this month's problem. Until February,